The next topic we're going to discuss is molar mass. Now, before we actually get to molar mass, I want to briefly discuss another term that you've probably never heard of, at least not very common, but it does kind of relate in the chemistry concepts that we're talking about right now. So if I use the phrase dozen mass, we kind of say, okay, I never heard of that before, but it kind of makes sense. Okay, the mass for 1 dozen of some objects, or the mass for 12 of some object. Well, again, in chemistry, we're not going to use the dozen number. Instead of dozen, we've learned, we're going to use the counting unit moles. So the same concept applies here. We have the mass for 12 of something, or we have the mass for a lot of something. So in chemistry, instead of using the dozen mass, we use the concept called molar mass. And it tells us the mass in grams for 1 mole of an element, or the mass in grams for Avogadro's number of atoms of an element. So again, we can see the two comparisons between what a dozen mass tells us and what the molar mass tells us. Now, where is that number? Well, it's a decimal number on the periodic table. So we look at a periodic table and we see that decimal number on it. Now, there's kind of some things here that might come up that you got questions about. You know, it says on the periodic table atomic mass or maybe atomic weight. Rarely does it say molar mass. So how does this kind of tie into some things we already learned? Well, the problem that comes into play is from section 3.2, where we talked about the atomic mass units. Okay, that AMU scale, where we found a new way to represent the mass for 1 atom of an element, which is a very, very small number. So wait a second, this number on the periodic table kind of sounds like it represents several different things at the same time, which is correct. So let's kind of go back to what we did in section 2. So in section 2, we were able to take an atom, for example, oxygen, that has 8 protons, 8 electrons, and 8 neutrons. And from that chart in section 2, we were able to figure out its mass, looking up all those numbers of the mass for 1 proton, 1 neutron, 1 electron, and so on. From that, you know, we were able to get a kilogram number, we were able to convert it to grams, or we were able to take kilograms and go to AMUs. So let's say we did that calculation. So now we have two numbers. We have the mass for 1 oxygen atom is 2.65 times 10 to the minus 23rd grams. Which again, we go back to the whole concept of grams. That's a really not a very good number to manage. So they created the AMU scale. And the AMU scale says 15.96 AMUs. Okay, well, what if we had 10 oxygen atoms? Well, if we had 10 oxygen atoms, then it would be 10 times its mass for 1. If we had 100, it would be 100 times that. Well, what would be its mass in grams if we had this many atoms of oxygen? So I want you to get out your calculator and actually figure that out. If one oxygen atom has a mass of 2.65 times 10 to the minus 23rd grams, then what does 6.022 times 10 to the 23rd atoms have in terms of its mass? So when you do this calculation, and again, we'll just round it here to keep 2 decimal places for some consistency, it's going to come up to 15.96. All right, wait a second. 15.96 grams is the mass. Grams is the mass for that number of atoms. 15.96 AMUs is the mass for 1 oxygen atom. It's the same number, represents 2 totally different things. Let me give you a comparison. If I were to tell you the distance from here to Brunswick, Ohio is 12 miles, and then I tell you the distance from my smart board, 12 miles. Let me just kind of gave it away there. To give you a comparison, let's say the distance between our classroom and Brunswick, Ohio is 12. Then I tell you the distance from the smart board to the door is 12. How can they be the same number? Well, I didn't give you one piece of information. The units. 12 what? So yeah, they could be the same number. So here we have a relationship where one atom is 15.96, and a lot of atoms are 15.96. Well, it's our units. So as we're talking about this, here's what you need to think about to summarize it. The decimal number on the periodic table tells us the mass of one atom, if the units are in AMUs. It tells us the mass for 1 mole of atoms in grams, and it tells us the mass of that many atoms in grams. So remember, if you see the word atomic mass, we're knowing, okay, that's the number, and then units are AMUs. And if you see the term molar mass, then you know the units are represented in grams. All right, so a couple calculations here. Sorry, one more thing here, and then we'll get to that. So molar mass. Again, we see that what its definition is. How many grams are in 1 mole? How many grams are Avogadro's number? It's different for each element because protons, neutrons, and electrons aren't equal. And we're left with conversion factors. So all we need to know is how to correctly apply these conversion factors in our calculations. So let's say the first one, we do a calculation from moles to mass. Here's the conversion factor that we will use. So if I give a simple calculation here, we have 8.48 moles of silver. How many grams would that be? What would be the mass of that amount of silver? Well, we would multiply by our conversion factor. We have moles, we're trying to go to mass, so we need to know that the mass for 1 mole of silver is 107.8682 grams from the periodic table I used, over 1 mole of silver. Moles of silver cancel out. The mass for that many moles of silver, rounded to 3 significant figures, would be 915 grams of silver. Again, the number on the periodic table tells us how many grams are in 1 mole, but we have almost 8.5 moles. One calculation then, going in the opposite direction. Now we're going to go from mass back to moles. So what do we have here? Let's say we start out with an amount 19.2 grams of aluminum. Okay. Multiply by our conversion factor to go from mass to moles. So now we need to go to moles. So our molar mass is set up that 1 mole of aluminum is equal to its molar mass. So we flip the conversion factor. So now we start out with grams. We're able to cancel them out. Pick up our calculator. And again, just in these examples, I have a lot of 3 significant figure answers. 0.712 moles of aluminum. And again, as we're checking through that, it's good not to try and memorize multiply and divide is very tough. You start with the number you're given, set up the conversion factor so terms cancel. All right, so what I have here is 2 more, 1 of each type. So what I'm going to have you do here is suggest you pause it, work on these 2, and we'll come back and we'll go over the answers. Okay, so now if we look at these 2 calculations here, we have 4.87 moles of calcium, and we're trying to figure out how many grams of calcium are in that sample size. So we have 4.87 moles of calcium, and we are going to multiply by a conversion factor that relates moles to mass. And the conversion factor is the molar mass. So we're going from moles to mass. Right? So what we're going to have is we're going to have 40.078 grams of calcium are in 1 mole of calcium. Moles cancel. We do our calculation, significant figures, we should have a final answer with 3. So 4.87 moles of calcium is equal to 195 grams of calcium. In our second calculation, we have 4.25 kilograms of copper, and we're trying to figure out how many moles of copper. First of all, hopefully everybody recognized that it's in kilograms. So that would be equal to 4,250 grams of copper. Again, if you didn't, then your decimal is just going to be off a little bit. So we have grams of copper. Now we're trying to go to moles. Again, the conversion factor we use is molar mass, but now the conversion factor is flipped. In 1 mole of copper, the molar mass is 63.546 grams. We started with grams, so we're canceling them out. And in our final answer, we're left with the moles of copper that are in this sample. And rounded to correct significant figures, it would be 66.9 moles of copper. The two examples that we have done so far have dealt with moles and atoms, or atoms and moles, and now we've looked at moles and mass, or mass and moles. Okay, so we've looked again at moles and atoms and moles and mass. Well, the only combination left then is how do we relate atoms to mass? And what we end up having is now a two-step calculation, which we will cover in our next episode.